There is a
I could not follow this.
yes,
I find myself.
Even the
Okay, shall we start? So, today's lecture will be devoted to Heisenberg model at t greater than tc, and this is all part of local ferromagnetism in the chapter. Local theory of ferromagnetism. Okay, any questions regarding the previous lecture? So tell me where you are now in superconductivity. So what are you discussing?
Theory.
Ginsburg and Dow? So now you learn, well, I suppose you learned all the basics of theory of phase transitions. Namely, what's Landau functional, what's Landau theory, lambda phi to the 4, spontaneous series vibrating. Because we agreed with Professor Yevtushenko that we are not going to tell you twice things, so we rather proceed such a way that he will tell you about general things about phase transition, but I will give you some examples and also some complementary information. Did you look at semi-classics in the book? No. Do it. Do it. Semi-classics is one of the important things and very powerful tool with a lot of applications. Okay, today we proceed with the scheme I discussed during the last lecture. Namely, we discussed the Heisenberg model, isotropic Heisenberg model above critical point. We use a mean theory in order to calculate susceptibility as a response on non-uniform magnetic field, and then we discuss properties of this response function. Okay, then we start with a model described by the interaction Hamiltonian sum over n, m, I, n, m, s, n, dot, s, n. So we discuss isotropic model and just for your notations and again reminding you what we are doing, I suppose that all coupling constants I and m are positive. Therefore, the ground state of this Hamiltonian corresponds to alignment of all spins parallel, and this is called ferromagnetic ground state. For notations, suppose we have a given spin n equal to n node. So we fixed n. And of course fixing n means that we fixed Rn. The radius vector which connects the origin with a given lattice side. We have origin here, so this is n, and for making notations short, I denote this n. Suppose we have a simple cubic lattice. Then we have 3 axes, and as you see, these are in 3-dimensional cube are nearest neighbors to given spin. So, if INM is equal to I for n minus m is equal to A, where A is a lattice constant, and 0 otherwise, then we speak about nearest neighbors interaction. Nearest neighbors interaction. Sometimes in the literature they are denoted as NN, or in some people write NM in the bracket. So this tells us that only nearest neighbors are assumed to interact. And for this example of simple cubic lattice, you see that for any given spin, there are 6 nearest neighbors. If we have square lattice, so we have a planar magnet, and of course, for making cartoon, it's much more easy to do it on a plane than to do it in 3D. So again, if we fix some spin, then we have 4 nearest neighbors. But although the matrix element, which defines arm exchange as exchange integral, is decaying, and this is matrix element of interaction taken with wave functions, sometimes it happens that not only nearest neighbors, but next to nearest neighbors interact. So what does it mean? Let me take the color chalk. Then for simple cubic lattice, these are spins which are next to nearest. So if we define our model such a way that I n m is equal to I1 for n for nearest neighbors, I2 for n and n stands next to nearest neighbors, so nearest neighbors, so next to n and 0 otherwise. Then we discuss a model where both nearest and next to nearest neighbors interact. And then you can include more and more neighbors. Again, if you want to include next generation of spins, what you have to do is to take this one, so then you can make your model more and more complicated. So for simple cubic lattice, somehow you see that both number of nearest neighbors, next to nearest neighbors, and next to next nearest neighbors is the same. And this number is equal to 4. Of course, for 3D simple cubic lattice, it's not the case. And just as exercise to check how good you understand the crystal structure, try to calculate the number of mixed to nearest neighbors for simple cubic 3D lattice, or you know the answer. If you know it by heart, tell me.
8.
No.
6.
Not 6. 6 is number of nearest neighbors. 12 is correct. But check it. I might be wrong. You can draw it and calculate. Okay, as I said, if all exchange integrals are positive, namely this way, you see that there is no contradiction, that all spins want to be aligned, so both this, and that. But anyway, the total structure of alignment tells us that in the ground state, namely at 0 temperature, and today we are not discussing 0 temperature, it will lead to ferromagnetic state. If somehow we discuss a model when one of exchange integral is negative, it also can happen, because the matrix element with wave functions is not necessarily positive, then we have more complicated structures. Okay, it's also instructive to introduce a magnetic field to this model. Suppose we have uniform magnetic field. And if field is applied in some direction, we're now free to say that our z direction is along magnetic field. So we say that H is equal to, say, H node times Z. So therefore our z-axis will be parallel to magnetic field. Then we can write down the Hamiltonian corresponding to interaction of spin in the lattices with uniform magnetic field. Field is equal to minus G mu bar A sum over N S N Z. This is nothing but scalar product the Hamiltonian, which we used in 2 lectures discussing both classical, semi-classical and quantum model. Okay? Then let's define a Fourier transform of spin, because we will apply Fourier transform, write down the Hamiltonian in Q representation, and then work with the Hamiltonian in Q representation. So, in order to do it,
excuse me, we use monotone bar, so does mean we are dealing with spin electrons?
yes, there is no L. Good question. So before I wrote as G, JG, and it corresponds to the situation J is equal to S plus L. For the moment, let's say that we are in the situation where there is no orbital magnetism, therefore J is equal to S, and Gj is equal to G. This is my definition.
Can you give an example, a real example for some substance?
Described by this Hamiltonian. Well, there are many ferromagnets subject to Heisenberg model. And Heisenberg model, isotropic or isotropic, is good approximation for this kind of magnetism. The point is that I hesitate to tell you that iron or nickel or cobalt is precisely the system which described by this Hamiltonian, just due to the reason that the magnetism of these systems is more complicated phenomenon. But what can I say you if you want to know a precise example? Let me answer your question next time, because I don't want to provide you incorrect information. I will give you some examples. But reality is, you know, that if you ask me what the system is described by Ising model, it will be a very complicated question. I can say that in some approximation, lithium fluoride systems are subject to this model, but real life is more complex, so to say. Such kind of simple models being a good approximation for general properties of system sometimes are too simple to describe quantitatively, not only qualitatively, the real system. So today, and in the course of local theory of magnetism, we discuss qualitative phenomena. Such kind of sometimes symmetry breaking, correlation length, but in order to make a quantitative agreement, one needs to proceed with more with a model containing more parameters. Today we will be dealing for the most of the lecture with a model describing just nearest neighbors interaction. Okay. Yeah. The Fourier transform SQ is defined as the integral over dr e to the power minus I dr s r, but s is localized on the lattice side, therefore we can write it down that this is sum over n. So SR is proportional delta function R minus Rn. So we have to take summation over all Rn. Let me write it on the next line. So it's sum over n integral over dr e to the power minus I dr s n delta function R minus Rn. So then I'm fine to plug in R from the delta function, and by the definition it's sum over n f n e to the power minus I q Rn. And okay, in order to give you flavor of different notations, today I will include the total number of spins in a system in inverse Fourier transformation. So I will make Fourier transformation asymmetric, namely Sn will be defined as 1 over n, total number of particles, sum over q, s q e to the power I q r n. So this is how direct and inverse Fourier transformation is defined. Tomorrow, discussing magnons, we will make this transformation symmetric, normalizing both of them on 1 over square root of n. Okay. So, we have our Hamiltonian. Suppose first we don't have magnetic field. It's sum over n m I n n s n dot s n. Okay? We take this one and plug it in the formula. So this is minus sum over n m I n m 1 over n sum over q1, 1 over n sum over q2, s q1 SQ2, and then there is exponent e to the power I Q1 Rn plus I Q2 Rm. Okay? So far so good, but then we recall that INN depends on modulus Rn minus Rm. Therefore, instead of making summation over all lattice sides, it's better to redefine our summation. Namely, introduce new variable rho such a way that Rn is equal to Rm plus rho. Then INM depends just on modulus rho, so I will denote it as I rho. I continue the line here, so summation will give a minus sum over m, sum over rho, I rho 1 over n squared, sum over q1, q2, sq1 dot sq2 e to the power I. Now I substitute this one, q1 plus q2 Rm plus I q2 rho. Q1 rho. Okay? But you see that Rm comes only here. Nothing else depends on Rm, and we know that sum over m of exponent to the power iq Rm gives us number of sides times Kronecker symbol q1, q2. So this is minus sum over rho, I rho. What I said is sum over m e to the power I q R n is equal to n delta function q0. Okay? So using this property, we have 1 over n here, because 1n is cancelled out. We have sum over q1, q2, sq1 dot sq2, delta function q1 minus q2, and then exponent I q1 rho. So what remains is minus sum over q. I will denote q1, q2 equal to q. Then it will be s q dot s minus q, and here times sum over rho 1 over n I rho e to the power I q rho. I will denote this constant as iq, and therefore it is equal to minus sum over q, iq, sq times s minus. So this is a Hamiltonian we are going to deal with. Okay? Do you understand what is done? So, let's look at IQ. It's 1 over n sum over rho I rho e to the power I q rho. Let's start with a model of 3D simple cubic lattice with nearest neighbors interaction. Then all i's, so I rho is equal to I if rho is equal to A and 0 otherwise. Then IQ for this model can be easily calculated. It's sum over n. So now I have to take summation over all nearest neighbors as it is written. Q rho takes value plus and minus a in the direction x, y, and z. So it is equal to I. When I take a direction x, then it is a qx a plus e to the power minus qx a. Plus, I take a direction y. So it will be x, sorry, y and z. E to the power I q y a plus e to the power minus I q y a. And the same for z direction. Plus e to the power a q z a plus e to the power minus I q z a. And that's all. Of course, I can take anisotropic lattice with the diagonal symmetry, and then I can assume that the lattice constant, A is a lattice constant, in x, y direction is different. For example, it is equal to A1 in x direction, A2 in y direction, and A3 in z direction. Then I will just substitute proper lattice constant in the direction. So simplifying this formula, I can write down that it is equal to 2 times I over n, and here there is a cosine qxa plus cosine q1a plus cosine qza. I will use the form of this exchange integral later. So what do we see from this formula? And what is actually obvious even from general expression? First of all, I, q is even function of q, equal to I minus q. Then I, q equal to 0. For example, if I take q equal to 0, I will get 6I over n. And 6 is precisely the number of nearest neighbors, or as it is sometimes referred to in the literature, coordination number. So if I denote z is a coordination number, then it is equal to I z over n. The problem which I would like you to recommend to solve is take first square lattice. I mean simple cubic lattice on a plane where there is no z component. Then of course for 2D version of the lattice you drop this term. So then there will be no this term, the total number of 2D component is 4. Again, the coordination number of square lattice is 4. So you come to this dependence of the exchange integral on a Q. But let me take the model with the both nearest and next to nearest neighbors interaction. Write down the IQ and see what it is equal to for that problem in the plane. And then, if you understand how things work, do it for simple cubic lattice in 3-dimensional case. Okay? Do you understand what the problem is? Fine. I'm not going to spend more time on that. Would rather like to proceed further. The important message that the function is odd, the function is even, and we have a coordination number in front. So, uniform magnetic field. As we saw, the Hamiltonian field is equal to minus G mu bar H sum over N S N Z. This is the same as minus G mu bar A sum over N S N Z e to the power I 0 times Q times Rn. I wrote it explicitly to show you that it corresponds to Q equal to 0 response. So uniform response is nothing but minus G mu bar 8, and here S Z Q equal to 0. Because by definition, this is Fourier transform corresponding to 0 moment. Okay, let's assume that we generalize this model for the field which is not spatially uniform but non-uniform. So let's assume that H is equal to Ez times H times cosine Q null R. What does it mean? That field changes in space such a way that it goes from 0 through 0 value. So we make our field being modified in a space in its value such a way that it can take positive and negative sides. And I'm going to study a response on that field where Q naught is fixed. In particular, if Q naught is equal to 0, we have a uniform field. This is a generalization of the field in order to calculate response functions. Okay, then, of course, H field is equal to minus G mu bar 8 sum over N S N Z, and here I will write cosine as a sum of two exponent I Q node R M plus e to the power minus I Q node R M. So this is nothing but minus 1/2 G mu over 8, and what we have here is S Q node Z plus S minus Q node Z. So our field actually selects us two Fourier components, which then are talking to the field. Okay? Good. Our Heisenberg integral interaction is minus sum over Q I Q S Q S minus Q plus H Q. But you see what happens. The field is talking only to two components, Q and minus Q. We are dealing with a situation the temperature is above critical temperature. Therefore, our magnetic field can only be responsible for the magnetization proportional to the field for the components where Q is equal to either Q node or minus Q node. So I would say when this field is applied, then S Z Q node average is proportional to delta, sorry, SQ average Q minus Q node, while S minus Q Z average is proportional to delta Q plus Q node. And there is no magnetization in any other directions because the field is applied in Z direction. So the approximation, I will write it down. Approximation mean field is, let's replace our Hamiltonian, which is exact, to some approximate Hamiltonian in a way that we will write H mean field, standing for mean field, is equal to minus I Q node S Z Q node S Z minus Q node plus, sorry, minus I minus Q node S Z Q node S Z minus Q node plus HP. So what I did, I said that my magnetic field actually results in this response affecting only Q node component. And since among all Q only this component survives, I'm replacing it by average number, but of course I have two spins, therefore I have to do it twice, namely I have to do it for this guy and that guy, and therefore this mean field Hamiltonian can be written down. In the spirit of what we have discussed before, it's pretty the same. We are telling that one particular spin is talking to all other spins, and we replace the back action of other spins on a given one by the mean value. Okay, let's now see what do we have with the magnetic field. I would like to write it down in a way of the Hamiltonian where spin is subject to some effective magnetic field, the same way as we have done for treatment with a Boolean function. So let's collect terms. I probably erase it here and write it down minus 1/2 G mu Bohr 8 times S minus mu node Z minus 1/2 G mu Bohr 8 S mu node Z. So you just replace these two terms and wrote it one by one. Therefore, you see that these terms and that terms can be combined such a way that we have effective field H effective expressed in terms of our external field. So the effective fields which act on component Q node and minus Q node will be written down. But one remark here, we use the fact that our exchange integral or its Fourier transform is even function of the moment. So in principle, instead of writing minus Q node, I can equally write plus Q node here. So effective field is, first of all, I will write 1/2 G, 1/2 H plus I Q node divided by G mu Bohr times S Z minus Q node. So this is a field which acts on a projection Q node, and in principle, since we are dealing with extensive values, I will multiply it by the volume of system. The same way, so this is what acts on S Z Q node, and the same way H effective acting on the minus Q node component HV plus I Q node over G mu Bohr S Z minus Q node V. But as you will see from the calculations, of course, both plus and minus Q node are the same. So therefore, field is pretty the same, acting both on plus Q node and minus Q node direction as it is here. So now I have to recall my definitions of susceptibility. What is done actually, that I was dealing with this model. But I replaced it by the model which of the sort minus m times h. So instead of having interacting system, now I represent it as non-interacting system where field is replaced by effective field. Okay? So I dramatically simplify the model. So I include all effects of interactions on a mean field level into the definition of effective field. But for that model, we know that susceptibility chi node, which is limit of average magnetization of Q node component over H effective goes to 0, is nothing but susceptibility of non-interacting fields. It is what is given by QE law. It behaves as a C over T. we have done it by direct calculation of this susceptibility. However, the true susceptibility, of course, this one doesn't depend on Q naught at all. The true one, H, which depends on Q naught, is a limit over mz u naught over H external, or just H, where H goes to 0. So this one does depend on the field. So this is response on applied external field. This is the susceptibility of our effective model, where we are talking about non-interacting spins subject to some effective magnetic field. Okay. Let's now do the calculations. So our mz u naught is equal to chi naught times H effective. So it is equal to, since I am talking about Q naught, I will write 1/2 chi naught H beam plus I Q naught over G mu bar S Z minus Q naught times B. But on the other hand, it is equal to, since mz is it's a chi naught G mu bar S Z Q naught. So as I said, physically, the average magnetization for Q naught and minus Q naught is the same, because as I said, physically field is the same. Therefore, I will not care about sign plus or minus here anymore, and will remove minus from here. So if I combine these equations and express G mu bar S Z Q naught from here, it is 1 minus I Q naught V divided by G mu bar square, okay, times chi naught is equal to 1/2 chi naught H. The same way, G mu bar S Z minus Q naught, since it's practically the same, 1 minus I Q naught V chi naught divided by G mu bar square is equal to again 1/2 chi naught H. So if I now sum up these expressions and divide by magnetic field, as it should be here, I will calculate susceptibility as a response on non-uniform magnetic field. So I will use this definition. Unfortunately, this blackboard is much smaller than the one which we had in lecture room B. So I Q naught is equal to 1/2 and 1/2 give me 1 chi naught V divided by 1 minus I Q naught V chi naught divided by G mu bar square. So we calculated Q-dependent susceptibility, which depends on the wave vector corresponding to non-uniform action. So what I do now, I assume that my field can be expanded on all harmonics. I calculated response on one harmonic, only one harmonic. If the field has all harmonics, not only Q node, what I do, I will just remove index node. So again, you should understand the logic. I have some uniform field. I can expand it in Fourier transform, which will be containing all possible wave vectors. But in order to find a response on all possible vectors, knowing that Fourier components do not talk to each other, I have a quadratic Hamiltonian. I did it for one Fourier component and then saying that all other do the same. I'm arriving at this expression. Let's look at this expression more carefully and see what this expression tells us and how the response function looks like. Did you understand my derivation? This is very important. We come to this point discussing response function, for example, in Coulomb gas, the electron gas interacting, for where interaction between electrons is described by Coulomb interaction. And then we rederive the same kind of formula with a method which is called random phase approximation. So in this sense, mean field approximation and random phase approximation is the same, but that time we will discuss the physical reason and the physical origin of the word random phase approximation. So at this moment, if you see somewhere REA, which stands for random phase approximation, so this is equivalent to mean field approximation of the system. We will come to this point in more details later on. So, let's back to Curie susceptibility, because we know what chi naught is. I remind you that chi naught is equal to n over v s plus 1 over 3t times g mu Bohr square. Okay, let's plug in chi naught here. So what we get is that chi, and this is precisely c over t, the definition of Curie constant. So chi q is equal to n times s plus 1 over 3t g mu Bohr square, 1 minus g mu Bohr square cancels, so it's I q. V also cancels, so it is n times s plus 1 over 3t. So then, sometimes in the literature, the susceptibility per spin is discussed. Per spin. So this is 1 over n chi q, and this is, according to this formula, s plus 1 over 3t g mu Bohr square, 1 minus I q n times s plus 1 over 3t. But sometimes the susceptibility per unit volume volume is discussed. So if I divide it by the volume, it's n over v, s plus 1 over 3p g mu bar square, and denominator is the same. So it's 1 minus I q n times s plus 1 over 3t. Okay, let's take our favorite, beloved model of simple cubic lattice with nearest neighbor interaction. So IQ is equal to 2I over n, and here we have cosine QXA plus cosine QYA plus cosine QZA. And this, I recall you, this is nothing but sum over rho 1 over n I rho e to the power I q rho. Again, to let you be familiar with the literature, sometimes the total number of nearest neighbors, namely coordination number, is separated explicitly from this formula. So sometimes it is written z over n, and here, since I multiply it by z and divided by z, it's sum over rho I rho phi q phi, sorry. It's Zn I phi q, where phi q it's 1 over z sum over rho e to the power I u rho. So sometimes this, so it will be 1/6 of this cosine. So sometimes people write it that way, where phi q is called structural factor. Let's see how this function behaves at small q. So IQ goes to 0, and Q goes to 0 means that QA much smaller than 1 in all directions. We can expand. So if we do it, we write it 2I over n. Here, each cosine will give us 1. So it's 1 plus 1 plus 1 minus QXA squared over what it is, 2 minus QYA squared over 2 minus QZA squared over 2. Right? So in total, it's equal to 2I over n. Here we have 3 minus, I will write it as QA squared over 2. Or it is equal, if I take out 3, I will get 6I over n, and here 1 minus QA over 6 squared. Or it is equal to ZI over n, 1 minus QA squared over 6. Okay? So now I plug in this IQ.